Good morning, my dear students. I am in this class for Physics SS1. My name is Dr. Mrs. Okekepien. Our topic for today is fluid at rest and in motion. By the end of this lesson, the students should be able to define surface tension in liquids. Number 2, classify fluids according to their viscous properties. Number 3, give at least 2 examples of the application of surface tension and viscosity. So here we go. The molecules of liquids and gases are more free to move than those of solids. Hence, both liquids and gases are able to flow. For this reason, they are grouped together as fluids. So whenever you hear the word fluids, it means liquids and gases. They have no rigid shape and they respond to forces much differently than solids. So in this topic, we shall study such forces as surface capillarity, viscosity, and their applications. Now we talk about surface tension. Just as I told you that we are going to discuss surface tension, capillarity, and viscosity, we are starting with surface tension. Surface tension is the force acting along the surface of a liquid, causing the liquid surface to behave like a stretched elastic skin. There's another way you can define it. It is the force per unit length acting on the surface at right angles to one side of a line drawn on the surface. There's another option of the definition. It is the tendency of the surface of liquids to act like a stretched elastic skin. So among all these 3 options, you can take one of them, the one that is easier for you to define. Maybe you have been noticing this surface tension, for instance, when after making stew or making soup, you carried it down from the fire and allow it to cool. When you open the pot, you see something that will be like a nylon covering the surface of the stew or the soup. So that the nylon material you're seeing is formed to protect the whatever that is inside underneath the stew or the soup, and that is the formation of surface tension. So mathematically, surface tension is equal to average force over length. Average force, we have F over 2, signifying average, over length. And by the time you evaluate that, you'll be having F over 2L. So whenever you are calculating surface tension, you can use that formula F over 2L. And the SI unit is Newton per meter. Newton per meter. Dimensional that dimensional expression of surface tension. Before this time, we have talked about derived fundamental and derived unit. There we talked about forming dimension for some of the quantities. So we can form dimension for surface tension, knowing fully well that surface tension is force over length, but force equals ma. That is mass times acceleration. Acceleration dimension, we know it before now, that it is LT to power minus 2. So having it together, we have MLT to power minus 2. Then length, we represent it by capital letter L. Therefore, substituting it into that formula of surface tension, we have MLT to power minus 2 over L. All these symbols should be in capital letters. Then, and that gives us MT to power minus 2, because L up and down will cancel out. Now, derived unit for that derived symbol for surface tension is kg, because m being the mass, unit is kg, t being time, unit is second. So we have kg second, kg per second square. Now, factors that affect surface tension. We have number 1, temperature. Number 2, nature of liquid. Number 3, impurities. And number 4, the medium in contact with the liquid. Effects of surface tension. This can be observed. Number 1, when water is allowed to drip slowly from a tap, the shape of each drop is spherical, as in the figure below. You can see the shape in that diagram below. Number 2, when mercury spills on a glass surface, it forms spherical droplets, as in the diagram below. You can see it, the drops of mercury on a glass. Once you drop it, it forms bubbles on that glass. It is as a result of surface tension. Number 3, water wets glass as a result of surface tension. You can even practice that one wherever you are now. You pour water on the table. You see how the water will just spread and wet the table or the glass. But if it is mercury, it will just form bubbles and roll down. Number 4, soap bubbles are spherical in shape. Soap bubbles. Some of you are fond of, when you make soap, you form bubbles and you'll be blowing it like balloon. You see how it will blow out in a spherical shape. It's as a result of surface tension. Number 5, capillary rise. Number 6, pond scatter, or we call it insects. Insects, pond scatter, are able to walk on water surface or floating of razor blade or dry needle placed with care on the surface of a liquid. All these ones forms one point. If you have mentioned pond scatter are able to walk on water surface, you need not to mention floating of razor blade or dry needle. So you, out of these 3, just pick one. They are speaking the same thing. Number 7, water does not penetrate umbrella as a result of surface tension. Number 8, bristles or hairs of a brush stick together when removed from a liquid. You can practice all this even at home, and you notice the same thing. Now, methods of reducing surface tension. How can we reduce this surface tension? Number 1, addition of impurities, e.g., soap, detergent, oil, grease, camphor, kerosene, methylated spirit. So any of them you can you don't need to say example or method of reducing. You will now write like a soap. That is not a method. We say it is the addition of impurities, and one of the impurities is soap, or you can use detergent. All these are the impurities. Number 2 method, heating or increase in temperature or boiling. Any of the 3 you can pick. That's the 2 methods you can use to reduce surface tension. Then application of surface tension can be seen in number 1, the product of raincoat or tent or umbrella. That's where you see this application of surface tension. Number 2, capillarity action. Number 3, detergent or camphor may be applied in ponds and stagnant water in order to kill mosquitoes or reduce surface tension. So these are the applications. Now, calculation. Let us look at how we can make use of that surface tension formula. This is a question here. Calculate the force required to lift a needle 6 cm long off the surface of water if the surface tension of water is 3.7 times 10 to the power minus 2 Newton per meter. Solution. As usual, write out all the information given to you. L equals 6 cm. Convert it to meters. Convert it to meters. You will have 0.06 meters. Not cm here, 0.06 meters. So you can correct that unit there, 0.06 meters. Now, surface tension, 3.7 times 10 to the power minus 2. 3.7 times 10 to the power minus 2 Newton per meter. So you've written out all the information given. You are asked to calculate the force. F equals question mark. Now quote the formula for the surface tension. F over 2L. Do your substitution. First of all, make F the subject of the formula. You have surface tension symbol there, times 2L. Now do substitution. 3.7 times 10 to the power minus 2 times 2 times 0.06 equals 0.00444. Put it in standard form. You have 4.4 times 10 to the power minus 3 newtons. Is that okay? We move forward. Capillarity or capillary action. What is this all about? This is the tendency of a liquid to rise or fall in a narrow tube. The demonstration is shown in the diagrams below. You can see the 3 diagrams there. The first one is diagram A, B, and C. In that diagram A, you can see the tubes are of different sizes. The narrower one followed by this, and then the wider one. You see the level of when it is water, you see the level is very high in the narrower tube and the lower in the bigger one. When it is soap solution, you see the difference there again. But when it is mercury, it is higher in the wider tube. Now, observation. In diagram A, water rises in the tubes, but the narrower the bore, the higher the height to which the water rises. 2. In diagram B, we observe a similar situation, but the levels of soap solution in the tubes are lower than those of water. 3. In diagram C, the mercury falls in the tubes. The narrower the tube, the lower the mercury level. So all these are the observations from the diagram. Note, in both the water and the soap solution, the surface of liquid or its meniscus curves upwards. If you don't want to call it, if you don't want to use the sentence as it is, you can make use of the one in the bracket. I said here, it has a concave meniscus. A concave meniscus. So both the water and the soap solution have what? Concave meniscus. But in mercury, the meniscus is curved downwards away from the glass tube. Or you can put it together as the one in the bracket. I said that is, it has a convex meniscus. In fact, with this, you can even make out the difference between when it is water and when it is mercury. 2 terms, cohesion and adhesion, will be used to explain this capillary action. Cohesion is the force of attraction between molecules of the same. You can see that I underlined the same kinds, e.g., the molecules of water. So cohesion has to do with molecules of the same kind. Like that, we have taken example to be water, or molecules of water, they are of the same because they are all water molecules. Take note of that. Then adhesion is the force of attraction between molecules of different kinds. You can see I also underlined different kinds, e.g., the molecules of water and the glass. You can see water is of its own, glass is of its own, and all of them are made up of molecules. So they are of different kinds. Cohesion and adhesion explain so many things which we are going to look at now. Number 1, the different action of water and mercury when spilled on a clean glass surface, as shown in the diagram below. When you are looking at this diagram, you can see that mercury forms bubbles, just as we have said, but water wets the glass. So why is it like that? He said this mercury does not wet glass because cohesion force is greater than adhesion force. You know, they are all poured on glass, so but mercury does not wet that glass. Instead, it forms bubbles. Why? It's because the cohesion force of mercury is greater than the adhesion. Remember cohesion and adhesion, the underlined. Now water wets glass. Why? Because adhesion force is greater than cohesion force. So the diagram is self-explanatory. Now number 2 thing that cohesion and adhesion explain. Number 2, why a blotting paper absorbs ink. Number 3, water rises in the stem of plants. Number 4, liquid candle wax rises up the wick of a candle, or kerosene rises up the wick of a lamp. Because we are always surprised when we put on our kerosene lantern or our stove, kerosene stove, and you will be imagining how come the kerosene is moving up for to catch up with the fire you will put. It is as a result of that capillary action. Number 5, a drop of water remains for a time on the surface of a dry cloth before being absorbed, but a similar drop on a damp cloth is rapidly absorbed. You can even try that wherever you are now. A dry cloth, pour a drop of water on it, and then wet the other cloth and drop the same drop of water, and you will discover that the one on the damp cloth will soak immediately before the one with the dry cloth. Cohesion, adhesion, and surface tension forces are responsible for the capillarity of liquids as shown in the diagram below. The diagram is self-explanatory. That's water rises up a capillary tube. You can see it there. Another point we're going to look at is the adhesion of mercury to glass is much less than the cohesion of mercury molecules. Hence, mercury is depressed in capillary tubes as shown in the diagram below. Look at it there in that diagram. Mercury is there involved. Mercury is depressed. Okay. Factors capillarity depends on. You can be asked to mention the factors. Number 1, cross-sectional area of tube. How does it affect it? He said the narrower the tube, the greater the rise of liquid in it, but the lower the mercury level. Number 2, surface tension. So these are the 2 main factors that capillarity depends on. Now we look at viscosity. That is friction in fluids. This is the internal friction between layers of a liquid or gas in motion. It decreases with temperature and varies with the nature of the liquid. Liquids which pour slowly are said to be more viscous than those which pour faster. For example, cold, thick palm oil is more viscous than very cold water. Honey or engine oil are more viscous than water or kerosene. Also, when a stone or a ball bearing is thrown down a cylinder of a viscous liquid, the downward motion of the body is opposed by the viscosity of the liquid. Hence, the viscosity of the liquid is directly proportional to the motion of the stone. Experiment has also shown that the liquid frictional force F is proportional to the viscosity. You see the symbol there of the liquid. We will mention, we will know the name of that symbol as we move forward. The radius A of a ball and the velocity V at which the ball is falling through the liquid. Now in symbol, F, that is force, is directly proportional to AV. A being the radius as we have atomized up there, and V, the velocity. Removing the sign of proportionality, replacing it with a equality sign, you have to put a constant. That symbol there, AV. The name of that symbol is eta. So you can make eta the subject of the formula from that expression to have force all over area times velocity gradient. Now let us use that formula to solve an example. Given that oil viscosities at 0.15 and that of grease is 3 times the square root and the raised to power 3 of the oil, what is the viscous value of the grease? How can we solve this calculation? You use the formula of viscosity of grease, which is equal to eta times radius times V, that's velocity, equals root 3, because the question said is square root. Root 3 times 0.15 all to power 3. Simplifying that, you have 0.671 to power 3, and eventually the answer comes out to be 0.30. It has no unit. Motion of a ball thrown through a viscous liquid. Motion of a ball through a viscous liquid. You can see that diagram there. The ball thrown into that viscous liquid. The weight of the ball is dragging it down. The viscous force is trying to push it out. Upthrust is also trying to push it out. A ball bearing falling through a viscous liquid, such as engine oil, is acted upon by 3 forces, namely its weight, that's mg, the viscous force, that is V, which opposes motion, and the upthrust, U, which is due to the liquid displaced. The equation of motion is given by the mg minus v minus u equals ma. When the ball bearing attains uniform velocity or terminal velocity at the stage A equals 0, then that expression will change to become mg minus v minus u equals 0. Because the acceleration is already 0, therefore that ma turns to become 0. Make v the subject of the formula in that expression above. You have mg minus u. Look at that graph. The graph of velocity against time. It is there we have that terminal velocity. You can see from the beginning, from the origin, the object was moving with that acceleration a, and at a uniform velocity it curved, and that is where we have that terminal velocity. Note, raindrops whose motion is opposed by the viscosity of air attains a terminal velocity before reaching the ground. Also, any object released from an aeroplane attains a terminal viscosity before hitting the ground. Now, let us look at the differences between this friction and the viscosity. We have so many differences in that table there. Number 1, under friction, it does not depend on areas of surfaces in contact. Under viscosity, it depends on areas of surfaces in contact. Number 2, under friction, it is independent. It is dependent on normal reaction. It is dependent on normal reaction, but viscosity is not. Number 3, friction occurs in solid, whereas viscosity takes place in liquids and gases, which we call fluids. Number 4, friction does not depend on the relative velocities between two layers, whereas viscosity depends on the relative velocity between two layers. Now let us look at their similarities. Both forces oppose relative motion between surfaces. Number 2, both depend on the nature of the materials in contact. So these are the two similarities for that friction and viscosity. Now, application of viscosity. Number 1, viscous oils, grease, and air under pressure are used as lubricants because of their viscosity. Number 2, the viscosity of oils and greases decrease with temperature. Hence, their lubricating effects are lowered at high temperatures. Water is not used as lubricant because it has a low viscosity. Take note of that. Number 3, it is because of the viscosity of the air that the bulb of a swinging pendulum comes to rest more quickly with a cord attached to the string than without a cord. So all these are the applications. Now let us look at the effects of viscosity. Number 1, it reduces the rate of flow of a liquid. Number 2, it reduces the motion of a body in a fluid. Number 3, it reduces or prevents wear and tear in machine parts. So these are their effects of viscosity. Now, I think from here, that's end that topic. Now, assignment. Number 1, define surface tension. Number 2, mention and explain 4 effects of surface tension. Number 3, calculate the force required to lift a needle 12 mm long off the surface of water if the surface tension of water is 8.4 times 10 to the power minus 2 Newton per meter. Remember that you have to convert that millimeter to meters. Number 4, explain the terms cohesion and adhesion. Thank you for listening and stay safe. By the grace of God, we will soon overcome this pandemic. In Jesus' name, amen.
Wonderful.